Big me.
Big Rico.
It's Big Dr. Rico.
I'm not going to comment on that one.
That sounds like a TV show.
Or you know, the other type of show.
Okay,
You have
so
to make it weird.
let's do a circuit transfer function from the input-output differential equation given here. Okay? So, as I know you've all watched the lecture, we can do this by inspection. Okay, so we can write that the transfer function h of s is equal to the output Laplace transform, so VL of s, divided by the input Laplace transform, which is equal to, in this case, a fraction, which has the numerator coefficients are going to come from this side, because Vs is divided out here and brought to the left-hand side, and VL is, after the Laplace transform is taken, able to be factored out of this side. So we have VL over Vs on the left-hand side, and on the right-hand side we have whatever remains when you take out the Vs, and whatever remains over divided by whatever remains on the left-hand side after you factor out VL. So let's do that. We take this L, and we take the second time derivative, which in Laplace terms is s squared. In the denominator, we take L, we take s squared from the second time derivative, plus r times s, because there's a single time derivative, rs, plus this last term we have 1 over c, and we have just 1, right, the 0th time derivative of VL. So no time derivative there, so VL just factors out directly. So that is our transfer function. Okay? So you can go back and forth from a transfer function to an input-output differential equation, and from an input-output differential equation to a transfer function using this inspection method. You could go through the entire derivation where you take the Laplace transform, you ignore the initial conditions, etc., but that's not recommended when you can just get there. After seeing the derivation once, you can just do it by inspection. Okay, so that was the first example. The other example, two other examples actually. So this one, we're going to go from a state space model to the matrix transfer function. So I gave you an equation for this, a formula. The matrix transfer function is equal to the C matrix times Si, where I is the identity matrix, minus A, where it's the A matrix of the state space model, inverse B plus D, where these are the A, B, C, and D matrices of the state space model. So it's plug and chug, but that plug and chug is a little bit involved. So let's go ahead and plug it in. The C matrix is the identity matrix, right? 1, 0, 0, 1. We've got Si minus A, which I guess I'll do two steps here. Si is going to be S, 0, 0, S, right? Because scalar multiplication of S with the identity matrix gives us an S wherever there's a 1, and a 0 times S, or just 0 wherever there was a 0. Minus A, the A matrix here is negative 3, 4, negative 1, 1. inverse B, which is 1, 0, plus D, which is 0, 0. So what happens to something when you multiply it by the identity matrix? It just equals itself, right? So we can ignore this C because it's not going to change anything. It's like multiplying by 1. So we have remaining S, so this is an element-wise subtraction, S minus negative 3, or S plus 3, 0 minus 4, or negative 4, 0 minus negative 1, or positive 1, S minus 1, or S minus 1. Inverse times 1, 0, plus 0, but when you add 0 to anything, once again, it does not change. So this is like a softball one, right? Easy one. Okay, so we got to take this inverse. So the formula for this shows up in the appendix on matrix algebra in the Rowell and Wormley text. A 2x2 matrix inverse can be done symbolically pretty straightforwardly. Remember, we have to do it symbolically because we have these S's in there. So you can't use your calculator, probably. I mean, maybe you have a cool calculator that does this. If so, great. I don't care. You can use it. But probably not. So the formula is you have to do 1 over the determinant of the matrix, which is S plus 3 times S minus 1 minus negative 4 times 1. Could somebody shut that door for me? That'd be awesome. Thanks. And then the second part. Thanks. Forever on the internet hereafter. A former model. Okay, so we've got these, so the formula then goes, when you want to do this matrix inverse, you swap these two terms, S minus 1, S plus 3, and then you change the sign on the others, so negative 1 and positive 4 times 1, 0. And we can take this matrix multiplication. We can also expand out the denominator here. The denominator is S squared. We're going to get a plus 3S minus S, so plus 2S. And then we're going to get a negative 3 plus 4, or plus 1. And the matrix multiplication, it's a 2 by 2 multiplying a 2 by 1. The inner dimensions collapse, and we're left with a 2 by 1. It's going to be S minus 1 times 1 plus 4 times 0. So just S minus 1. And negative 1 times 1 is negative 1 plus S plus 3 times 0 is 0. So you could rewrite this. This is as simple as it gets, but if you wanted to make it look more like the two transfer functions that it represents, you could multiply the determinant term, this coefficient, through each term, S minus 1 over S squared plus 2S plus 1, divided by negative 1 over S squared plus 2S plus 1. So this is the transfer function output of the first output, y1 of S, over the input, u of S. And this is the transfer function y2 of S, the second output, over the input, u of S. So that formula is essentially plug and chug, right? If you want to go from a state space model to a transfer function model, you just plug it into that formula and work your way through it. The only issues that you're going to run into is you have to take a matrix inverse. You got to do some matrix multiplications, subtraction, not too hard. The inverse is the most challenging part. In this class, being able to do up to a 2x2 by hand on an exam in a short period of time is sufficient. What is the inverse of a 1x1 matrix? The reciprocal. So if you have the matrix, we'll call this matrix M, and you want to multiply it by its inverse, you have to get the identity matrix, right? If these are all 1x1 matrices, then this is, say, A times B equals 1. Multiplying a 1x1 by 1x1 just gives you the product of A and B equals 1, which just says, equating each of the components on each side, we get AB equals 1, which tells us that B equals 1 over A. So A inverse equals 1 over A. That was a little demonstration thing.
But the determinant's going to be 0, right?
No. No, the determinant's not 0. The determinant is the value of the is A. Determinant's A. Yeah.
Can you skip that over so I can see what you did on the last step?
This part?
Yeah.
So 1x1, reciprocal. 2x2, this little cute thing. 3x3, it'd be nice to know that off the top of your head. I always have to look it up. But
What is the practical application of this process to a system?
yeah, so there are many situations for which you'll want to know a transfer function. Many systems that having a transfer function model is helpful. The state space model is like kind of the best model you can have. The transfer function model is a good one, and it's useful for doing feedback control systems with simple ones. But what we're actually using it for in this case is we're using it as a bridge. We're going to be able to go from a state space model to the input-output differential equation that we already know how to solve directly, right? So that's mainly why we're using it as a bridge to the input-output differential equation. Question?
So the transfer function is just like transferring the domain, just like a Laplace transform?
Yeah, so the Laplace transform is the heart of the transfer function. So the transfer function is just a specific ratio of Laplace transforms. It's the Laplace transform of the output divided by the Laplace transform of the input. So it's a convenient way to represent a system's dynamics. So the input-output differential equation, that's the first one we learned how to do, right? The state space model is the next one we learned how to do. And then now we've got the transfer function as well, which we're using as a bridge between the two for now, and later we'll use directly. There's a lot of useful information in it. So it's one of the most common ways you'll see a system represented. When you look up a paper or from a textbook, if you find, like, here's a model for a system, a lot of times it'll be given as a transfer function. So we have to be able to use them, we have to understand them, we have to be able to transform them into other systems. So, and to transform our state space models into them if needed, which is what this example was about. So this first example, we went from an ODE, which is the input-output differential equation. we went to a transfer function model, right? This one here, we went from a state space model to a transfer function. And in this last example that we'll do, we're going to use kind of both of them. So we're going to go from a state space model to a transfer function model to the ODE, the input-output differential equation model. In the first example, we went this way by inspection, but by inspection, the other way is just as easy. So, yeah.
State space model is just the linear graph model.
Well, it's what we derived from the linear graph model, which is the ABCD matrices. So something of this form, right? Yeah, so this is the state space model. So we're going to start there on this one, start the state space model, which we know how to do by deriving a linear graph model of a system and then writing its state space model down. We're going to now use the transfer function to bridge us to an ODE, which that input-output ODE we know how to solve, which is why I'm showing you that bridge. It's useful to know about this, like to be able to change model representations. I just wanted to show you this so that you know, oh, okay, like if I wanted to solve this input-output ODE without having to deal with the state space model directly, I could do that. I could change it into an ODE. However, I will later show you in the system dynamics course next semester, at the very beginning of the course, we'll actually start with how to solve this. How do you solve this in state space form? So without transforming it into an input-output ODE. So we'll get there. So this one says for the following state space model, derived in from the circuit in the first example that we did. So it was the RLC circuit. Derive the input-output differential equations for each output variable. Now, I'm choosing 3 different outputs in this case. So I'm choosing IL, IS, and VR2 as the 3 outputs that I want. In the first example that we did, in that RLC circuit, I guess this wasn't. This was from example 3, 4, 1. I don't actually remember the example. It was like it was an RLC circuit with 2 resistors in it. Yeah, this is an R1 and an R2. So these are our 3 outputs, and we want to know what the 3 IO differential equations are. And this calculation is kind of involved. It's pretty messy. It just gets kind of messy. We'll just try to barrel right through it and get to the end. But recognize that I wouldn't give you guys one that required this much manipulation on an exam, but you should be able to do it when you're, chilling in your pajamas, drinking legal beverages for you to drink.
Hot chocolate.
Hot chocolate. That's what's legal. Yes. That. I was having a hard time coming up with one. But there we go. Or drinking coffee. Drinking coffee. Okay. So whatever you young people drink. Yes. Yes. So first we're gonna go from state space model to the transfer function model. Okay. So that's the same process that we just did, right? H of S equals C times SI minus A inverse B plus D. Okay, so the C matrix is this guy, right? This is the D matrix. So C matrix is 0. Actually, you know what? I'm not going to plug in these things. This is part of why it gets messy. I'm going to just say we have to do this inverse thing first, right? So instead of writing out everything 5 times, I'm just going to say C times I'll plug in SI, so S 0, 0, S for Si, minus the A matrix, which is a little bit messy, negative 1 over R1C, negative 1 over C, 1 over L, negative R2 over L. That was the A matrix that we derived in the previous example. Inverse B plus D. And we'll plug those in later when we're ready for them. So C times, now we can write this as, remember, element-wise subtraction here, S minus negative, so S plus 1 over R1C. 0 minus negative 1 over C, or 1 over C. 0 minus 1 over L, or negative 1 over L. S minus negative R2 over L, or S plus R2 over L. Okay, inverse B plus D. Okay, the inverse, we have to use that determinant here, so 1 over, it's this times this, so S plus 1 over R1C times S plus R2 over L, minus 1 over C times negative 1 over L, times, we swap these two on the diagonal, so we have S plus R2 over L and S plus 1 over R1C. Switch the sign on the other two, so we have 1 over L, negative 1 over C, B plus D. Okay. So I'm going to, we'll expand this out and then we'll call it something. So this is a scalar, right? It's a scalar value. So we can actually pull it out front of all the matrix multiplications. So we'll call it 1 over S squared plus, this is going to be 1 over R1C plus R2 over L S plus R2 over R1 LC. There's another term here. Plus 1 over LC. Okay? I'm going to call this denominator alpha. Okay? Not infinity. Alpha. Okay. Now this other stuff, we can start to plug in. So now we've got C. So the C matrix, we can plug in the C matrix. So we've got the C matrix, which is 0, 1, negative 1 over R1, 0, 0, R2. Okay, times the this matrix, so S plus R2 over L, negative 1 over C, 1 over L, S plus 1 over R1C, times the B matrix, which we'll actually do that one first because it'll simplify things a little bit for us. The B matrix is 1 over R1C and 0. So you can do this multiplication first or this multiplication first. I am going to do this one first because there's a 0 in here. It seems like it's going to help simplify things out. There are zeros in this other one too, so it's probably 6 or half a dozen. So we've got 1 over alpha times 0, 1, negative 1 over R1, 0, 0, R2 times now this product here, which is actually a 2 by 1, right? This is a 2 by 2 multiplying a 2 by 1. Interventions collapse and we get a 2 by 1. So we're going to get a, this term multiplies this, so we get 1 over R1C times S plus R2 over L plus 0. And then we get 1 over R1LC plus D. Okay, so now we have that multiplication to do, 1 over alpha, and we're going to get 0 times this plus 1 times that, so 1 over R1LC. And the next line is going to be negative 1 over R1 times this, so we have negative 1 over R1 squared C times S plus R2 over L, and then plus 0, right? And then 0 times that plus R2 over R1 LC. Plus, now we're ready for the D matrix, which is this, 0, 1 over R1, and 0. 0, 1 over R1, and 0. Okay, so, I mean, there's nothing to do but just plug it in, or just do the element-wise addition. So this first one comes out to be, we have 1 over alpha R1 LC. This one we have negative 1 over alpha R1 squared C times S plus R2 over L plus 1 over R1. And this one we get R2 over R2 over alpha R1 LC. So this is a 3 by 1, and each of these is a transfer function corresponding to each output. So I said the 3 outputs are IL, IS, and VR2. So we have here our IL of S over the input here. We should go back, but does anybody have the text or the notes for lecture 3-4 on them?
We didn't have a video for that problem, but we did an almost exact one in class.
Oh, great.
Yeah, it's this one right here.
Yeah, it was a current source.
Yeah.
Or what was it, a current source or a voltage source? Right. Sorry. Voltage source. It's a voltage source. We want to know the current from it. So our input here is Vs, which I probably should have repeated on this part. So if Vs is our input, that means that we have I L over Vs. That's our input of S. So that's the transfer function there. The second one is the transfer function from which it was IS, so the source current over the input, which was the voltage source. And finally, we've got, what was the last output? VR2. So we've got VR2 of S over Vs of S. Now, we don't really have time to do all three of these, but they're all the same procedures. So we'll just take the first one, and we'll write the input-output ODE associated with it. So we have a transfer function, which is, I'll just write it up here and I'll copy it down. I'm going to suppress the of S, over Vs equals 1 over alpha R1LC. So I'll copy this down, and we'll plug in alpha, because we've been suppressing that the whole time, right? So we have R1LC, we have S squared plus, and then I've got 1 over R1C plus R2 over L, 1 over R1C plus R2 over L, S plus whatever this term was, R2 over R1 LC plus 1 over LC. R2 over R1 LC plus 1 over LC. Okay. So, based on inspection now, we can back out what the ODE is, the corresponding ODE is. So, therefore, the VS term will end up on the right-hand side when we essentially cross-multiply here. And the IL terms will show up on the left-hand side. So what we're going to have is R1 LC, and then this is an S squared term. So we're going to have the second time derivative of IL of t now, dt squared, plus, this next one is fun, R1 LC times 1 over R1C plus R2 over L, and this is times S, so it's the first time derivative, dt of IL, the output, plus, now we've got R1 LC times this fun stuff, R2 over R1 LC plus 1 over LC equals, on the right-hand side, we just have 1. We could have divided both sides by R1 LC, would have simplified it a bit. Yes. Oh, yeah. Do I need an IL in there? Yeah. IL equals, the other side's just got a 1, right? So it's just VS. So this is an ODE, second order ODE, that we know and love. We could solve this, right? We could do that like the solution techniques from before. So I wanted to show how to do that bridge. And you could do the same thing to get a differential equation in IS and in VR2 or any other output variable we had chosen. Okay? So this sort of shows a little bit of the power of the state space model. Once you have that state space model, you can get any transfer function and any of the variables that you might want. A transfer function and differential equation corresponding to any of those variables. What we'll find is that the state space model is itself probably the best form that we can have things in. So we'll rarely want to do this, but I wanted to show you that we could, and it is a thing that we could do if we were wanting to get a differential equation in a specific variable. Later we'll learn how to solve the differential equation, the state space model, directly, which is superior in a lot of ways. Yeah, all right. Till next time.